Okay, in section 6.1, we're going to be taking a look at something called inverse trig functions, which we'll see eventually is actually a bit of a misnomer. But before we talk about those in particular, I want to just review what's meant by an inverse function. So I can sort of think of a function as a machine, where a function takes an input, it does something to that, and it spits out an output. Usually we call the input our x value, and the output would be our y value. So the trig functions do this. Our input is an angle. Our trig functions calculate a ratio associated with the angle, and that's the output of those functions. But some functions can be undone. They have what's called an inverse function. Inverse function. So that if I take an input and I plug it into a function and I get the output, and then I take that and I plug it into the inverse function, it does exactly the opposite of what this function did, and it loops back around and gives me that original input back. Great example of this is if I have y, or I could denote it as f of x if I wanted to use function notation, equals x cubed. The inverse function would be y equals f inverse of x. That's the cube root of x. Cubing something and taking the cube root undo each other. So if my original input was 2, and I plugged that into the cubing function, I would cube it, I would get out 8. That would be my output. If I plug 8 into the cube root function, it uncubes it, it gives me back 2. Okay. So that's a really nice property of inverse functions, that they undo each other. So that's one way I'm going to think of an inverse function. It's the thing that undoes whatever the function was doing. And the formal way that we express that is that if I compose them in either order, oops, I don't get 0, I get x back. So here I said if I take x, I plug it into f, so I do something, then I plug it into the inverse function, so I undo what I just did, I'm going to be back at x. And it works both ways. Whatever f inverse does, f undoes that, and it gives me back my original input. So that's one way I have of thinking about inverse functions. I can also think of them a little bit more graphically, because I can get inverse functions by just switching the roles of input and output. So let's suppose I had y equals x cubed. I'm going to think of that as my original function. What I'm saying is if I switch the roles of x and y, so if I write x equals y cubed, that's going to describe the inverse function. The reason that works is because in standard form, a function, we would solve it for y. So this isn't in standard form because it's solved for x instead of for y. So if I wanted to solve for y, I would have to say, I need to uncube that. How do I undo cubing? And so I would take the cube root of both sides. But of course, the cube root of y cubed is just y. Okay. So an inverse function, I can also think of it as it's what I get if I switch the roles of input and output. So if we switch the roles of x and y, or input and output. But there's an important caveat there, and that's that not all functions have an inverse. Not every function is invertible. And let me just give you an example. If I look at y equals x squared, and I think of this as the original function, and I try to find an inverse for it. Now, I'm going to fail because this function is not invertible. But if I were to switch the roles of x and y, so this would describe the inverse if it exists. So I would try to simplify and solve for y, so I would try to take the square root of both sides. But remember, the square root can never be negative. So this wouldn't be y, this would be the absolute value of y is the square root of x. And that would mean y is plus or minus root x. I would get two possible answers. And that makes it not a function, because for a function, if you know what you plugged in, there's supposed to be a unique output that you get. There's a right answer. You don't have, it's not multiple choice where multiple answers could be correct. A function is supposed to have one y value for each x value. So, since I don't get a unique answer, not a unique value for y, therefore not a function. Okay, so if I look at that graphically, I can sort of see what's going on. If I were to look at y equals x squared, the fact that that's a function is reflected in the line, in the fact that it passes what we call the vertical line test. Any vertical line would be picking out all the points in the plane that have a certain x value. And each one of those intersects the graph only once. That goes with each x has a unique y associated with it. But this function, even though it passes that test, it fails what we would call the horizontal line test. I can see if I were to draw a horizontal line, let's say at height 4, that would intersect this graph at two different places, at 2, 4, and at negative 2, 4. So even though each x has a unique y, each y doesn't have a unique x associated with it. So if I then switch the roles of x and y, I've now created a situation where each input, each x value, has more than one output, more than one y value associated with it, and so I don't have a function. Now, when that happens, we say that the function is not one-to-one. Okay. So some y values have more than one x associated with them. We could also say it fails the horizontal line test, and therefore we can say it is not invertible. Now, if I think about the graphs of my trig functions, they all fail the horizontal line test because they're all periodic functions. So whatever they do, they repeat. So y values are going to have more than one x value associated with them. So they're not going to be invertible. So it seems kind of weird that we've got this section on inverse trig functions when inverse trig functions aren't invertible. But I'm going to show you an example here with x squared that illustrates what we're going to do to deal with that. Okay. So here's the graph of y equals x squared. Okay. That is not invertible, fails the vertical line test. But what I'm going to, or fails the horizontal line test, I'm sorry, passes the vertical line test. What I'm going to do is I'm going to work with just part of that graph. I'm going to say, what if I look at y equals x squared, but I restrict the domain to make x bigger than or equal to 0? Because I can see the reason it fails the horizontal line test is because every time I intersect the graph on the right, I have a mirror image point on the left. Let's get rid of the left side. Let's just look at this. Now this passes the horizontal line test, so this is invertible. So this function, y equals x squared, is not invertible. Y equals x squared with a restricted domain is invertible. And if I wanted to find the inverse, I would say, okay, x equals y squared, But now y has to be bigger than or equal to 0. Because I get the inverse, remember, by switching the roles of x and y. So everywhere, in everything I wrote to describe the function, I had an x, I replace it with a y. And everywhere I had a y, I replace it with an x. Now if I do that, now I can take the square root of both sides. I still get the absolute value of y is the square root of x, but now if y is bigger than or equal to 0, the absolute value of y is equal to itself. Because when I take the absolute value of something that's not negative, it doesn't change things. So I would get the square root function is the inverse of the squaring function with this restricted domain. And that's the sort of thing we're going to be doing with inverse trig. We're going to say the function as a whole, if I work on its natural domain, is not invertible. But we're going to restrict the domain so that we can work with just a portion of the graph that does pass the horizontal line test. And that's going to be invertible, and that's the function that we're going to define. So that's where we'll pick up in the next video.